Welcome to this short video on Pascal's triangle, a beautiful gem in mathematics. Interestingly, Pascal's triangle begins with a simple idea. Place a 1 at the top, then build each new number by adding the 2 above it. From this modest rule grows a remarkable mathematical world filled with symmetry, number patterns, algebra, counting, and probability. Let's start with some questions. Look at this triangle. What do you notice? What do you wonder? And where do you see repetition, symmetry, or growth? Take a close look at the simple numbers as we define our vocabulary for this video. How is the triangle built? The rule is simple. Start with 1 at the top. Each inside number is the sum of the 2 numbers directly above it, while the outside edges remain 1. We use a naming system for rows and entries. The top row is row 0. We also count the position of each number on a specific row starting from 0 to. We write the entry in row n and position k as n choose k, which counts how many ways to choose k objects from n. Symmetry is a key feature. The left side mirrors the right. This reflects the combinatorial fact that choosing a team of 2 is exactly the same as choosing which 3 to leave off when there are 5 people total. By the way, there is one way to choose 5 from a group of 5, and also one way to choose nobody from a group of 5. Look at the second diagonal. It displays the natural numbers 1, 2, 3, 4, 5, and so on. This happens because there are exactly n ways to choose one item from a set of n items. The next diagonal reveals the triangular numbers 1, 3, 6, 10, 15, 21. They are so named because they represent the number of dots required to form an equilateral triangle. Here is why they are called triangular. By building one row at a time, we see the fourth triangular number is 10, because the sum of 1 plus 2 plus 3 plus 4 equals 10. Fibonacci numbers are hiding in the shallow diagonals. If we add the numbers along these paths, we generate the famous sequence 1, 1, 2, 3, 5, 8, 13, and so on. When we add the numbers in each row, we discover the powers of 2. Each new row doubles the sum of the previous row, moving from 2 to the power of 0 up to 2 to the power of 5 in the example. This is easy to see if you look at 1 plus 1 to the nth power in its expanded form. Pascal's triangle connects directly to algebra. Expanding the expression a plus b to the power of n gives coefficients that correspond perfectly to the entries in the nth row of the triangle. To see why a plus b cubed results in row 3, we look at the 3 factors. Choosing terms involves selecting either a or b from each factor, which follows the logic of combinations. The counting connection is clear through combinations. If you have 5 students and want to form a 2-person team, row 5, position 2 tells us there are 10 possible combinations. We can also count paths on a grid. If a robot moves only right or down, the numbers in the triangle represent the total number of unique paths to reach any specific point. Finally, consider the probability of flipping coins. If you flip 3 coins, row 3 gives the distribution of outcomes. The probability of getting exactly 2 heads is 3 out of 8. Let's look at the probability of 5 coin flips. Row 5 shows there are 32 equally likely outcomes. The probability of getting exactly 2 heads is 10 out of 32, which simplifies to 5 out of 16. We can also find unique patterns, like the hockey stick sums. By adding the numbers down a diagonal and then turning, the sum equals the next entry after the handle. Parity reveals a hidden design. If we shade the odd entries and leave the even ones white, a beautiful fractal pattern, known as the Sierpinski triangle, begins to emerge. This triangle is a bridge between worlds. It connects simple addition, algebraic coefficients, counting combinations, and probability distributions all in one single, elegant structure. To explain these patterns, try using sentence frames. For example, I noticed that, or the probability is out of. Encourage students to point to the numbers they are using before writing equations. To recap, Pascal's triangle reminds us that mathematics is not a collection of separate topics, but a network of connected ideas. A single pattern can lead us from addition to Fibonacci numbers, from binomial expansions to coin flip probabilities, and invite us to keep looking for the next hidden connection. Thank you for watching. We hope this video helps you appreciate the deep connections and beauty found within Pascal's triangle.